bastante a la sesión de la mañana. El segundo curso es sobre técnicas observacionales en astronomía y lo va a dictar el profesor Bernard Brown. El profesor Bernard Brown, aparte de haber tenido el honor de ser mi director de tesis doctoral, también es investigador, es profesor asociado en Leiden desde el año 2003. Hizo su doctorado en Grafing, en Múnich, y luego estuvo bastante tiempo en Cornell, la Universidad de Cornell, en Ithaca, New York, como investigador asociado, donde estuvo muy vinculado con el equipo que construyó y lanzó el instrumento del espectrógrafo del telescopio espacial Spitzer. Tiene una amplísima experiencia en instrumentación astronómica y es actualmente el investigador principal de uno de los instrumentos que va a ser instalado en lo que llaman el European Extremely Large Telescope. Y este instrumento en el que él trabaja es un instrumento en la longitud de onda del infrarrojo medio, se llama METIS, y él es el investigador principal. Aparte de eso, ha hecho muy buena investigación en formación estelar en galaxias, usando espectros del telescopio espacial Spitzer, y luego la oportunidad de hacer la tesis con él en cuestiones de espectros de Spitzer de regiones de formación estelar, galaxias, interacciones galácticas, starbursts. Entonces, de todo esto le pueden preguntar. Y bueno, creo que es además un muy buen orador, así que ojalá disfruten el curso. Entonces, Bernard, the audience is yours. Y bueno, ya saben, preguntas, if you have questions, just ask. English or Spanish is fine, we will translate.
You're German. You're German.
You're German.
Well, thank you, Rafael, for the thank you for the introduction. It's a great pleasure to be here, and let me extend my welcome also. I hear we have people attending remotely from Bogota and Bucaramanga, so also welcome there. Yes, so here are two courses, and they're highly complementary, as you'll find out. And the regular course, lecture course, this afternoon starts at 4 o'clock. And this is just an introduction. I'd like to introduce a bit of, well, the program, myself, but also what this course is about. And it's I think it's particularly necessary for that topic because this is not a course that you find.
I'm sorry for interrupting. Maybe you can talk from there in order to be the camera. You're not going into the camera, and we can use these two slides.
Oh, I already have that.
Sorry.
But,
so you can.
But then I will obscure your views, right? If I stand here, that was the reason.
But if you go here. We can ask for not.
Yeah. I mean, is it important to see me? I mean, it's important to see.
Okay. No, the presentation is in the it's already there. Okay. As you feel more comfortable. Please beside.
Okay, so the course is essentially sampling many different topics, all of which are relevant, but there are very few books or literature where you can find them. So this is your unique chance actually to learn about all of them. But let me start. Okay, why lighting? And of course, you know from Rafael that he has been my PhD student. He initiated the program. I guess if I ask people in Leiden to pinpoint to Medellin, they may not actually find the right spot. So I thought, well, just to be fair, I should also indicate where Leiden is. So obviously the Netherlands are here somewhere in Central Europe, and Leiden is a small city of about 130,000 people, just about 30, 40 kilometers south of Amsterdam. It has an old university. It has actually the oldest university in the Netherlands. This is just the academy building. There sometimes the Queen addresses the staff of the university or even all the students. well, and this is also where Raphael may remember that, right? This is the place of his historic victory, which resulted in the Dr. Martinez color sign. And then we have the old observatory here, which has been just recently renovated. It's a beautiful building and next to the water. We have many telescopes up here. But the astronomy department is actually in a completely new building. This is by design, but it looks like it's taking over. And yeah, and Light Observatory, as you mentioned before, has been the home for many, or at least quite a number of famous astronomers. So Frederick Kaiser is probably the one you know the least. But of course he was of local importance because he funded the observatory essentially. Without him there would be no Light Observatory. He also built the first telescope all by himself. So he was a sort of a self-educated astronomer actually. And he did great things, but he built the telescope on top of the academy building and then he developed it. There was one big figure here, Hendrik Anton Lorentz. So he's not the Lorentz who studied the behavior of the geese. He's the Lorentz who did all the electromagnetism work. And then followed by, most of them were also the directors of the observatory. Willem de Sitter, known for his work in cosmology. Einar Hertzsprung, was actually not Dutch, but Danish, but he worked at Leiden also as a director, and of course you know him from the Hertzsprung-Russell diagram. And there's Jan-Hendrik Oort, who essentially shaped most of the observatory in Leiden as it is nowadays. Well, he studied everything from galactic structure to our solar system. The Oort cloud is named after him. And then Henk van der Hulst, radio astronomer, who observed 21 centimeter light. And yeah, this is just a couple of the old things. And just to give you an idea how the city looks like, of course, Raphael's been there, maybe you'll have a chance to visit at some point. It's like a typical small Dutch town with lots of water and small bridges here, and well, in order to get sit outside, you actually have to have some pontons or boats here where people sit in the cafes, and then small bridges that have to open. It's, as you can see, it's all very difficult to travel, to get around by car. I tried once and I almost damaged the car because I was stuck here at this right point. But it's great for biking. And sometimes the canals freeze and then you can go skating. But last but not least, of course, the region is also known for all the tulips. So I hear you had Flower Festival yesterday. There are similar events in Holland. Most of those actually are not the plants themselves, they just cut it. This is a cruel event end of people. They come just with the machines and cut off all the blooming flowers because they only need the bulbs to ship around the world. Okay, so much about light. I should add here a few words of who I am. So I'm not the Dutch aboriginal, actually I'm from Germany, Nuremberg. So yeah, it looks a bit different. But what is more relevant here, of course, are my interests or my background. And there is one hand, there is systems that produce a lot of massive stars. A lot, I mean more than the Milky Way does on average. On average, our Milky Way just produces about one star, or one solar mass per year. Which, of course, yeah, I mean, the sun is quite important, so I don't want to downplay the one solar mass, but there are, of course, systems where tens or hundreds of stars are being born in a year. And I'm studying the objects like that. This is the nucleus of a galaxy at different wavelengths. I don't want to go into all the details, but this is fairly far away, so this is all limited by the available observing techniques. Right? What we need are more sensitive, more powerful, bigger telescopes working at more wavelengths in order to study these objects here. And as we've learned this morning from Elena, there is of course a lot of radiation transfer going on, which which is responsible for the apparent structure. So what you see here is, I mean, this is the nucleus of a galaxy. And then surrounding what's bright are massive young star clusters that produce a lot of light. And the contours here are actually the emission at 10 microns, so mid-infrared wavelengths. That's hot dust. So that's really a good example for radiation transfer, because all the light, the visible and UV light that is mostly emitted by those young stars, is completely absorbed by dust. It heats up the dust, and it is radiated here. And if you look, the background image, the color image is a Hubble image. If you look at these regions here, with Hubble you see nothing. So you really need to go to infrared wavelengths to see, you need the contour lines, to see, to get an idea of what's behind this curtain of obscuring dust. You can look at nearby objects, like this is the most massive H2 region in the Milky Way, W49, but it's also unfortunately on the other side of the galaxy. So in order to see that, you would have to look through the whole galactic disk, which of course also absorbs a lot of light, and so you will miss many photons at visible wavelengths, so you wouldn't see anything. So this is an infrared image again. This is an image of the Large Magellanic Cloud, and this is about 200 parsecs the side. And what you can see here is this amazing structure of the interstellar medium, where you have all kinds of filaments and little towers here of gas and dust. And that has been shaped by the clusters in here. So there were star clusters here, and then they evolve, and the radiation pressure and the stellar winds just move the material outside, and then you have this amazing structure here over hundreds of parsecs. And then we're looking at galaxies, how their appearance is in the infrared. This is for the first time, an infrared, or far infrared Hubble tuning fork diagram. I presume you know the basic classification of Hubble for galaxies with the tuning fork diagram, right, where you have your elliptical galaxies here, and your bar spirals here, and the regular spirals here. And then you can do, well, I realize you will not see that in the back probably, but you can find the diagram on the web. So it's just that the appearance is very different at infrared wavelengths, and of course you learn a lot by comparing their morphology in optical wavelengths with the morphology in infrared. So this is part of what I'm doing. And the other half of my professional life is instrumentation. And recently there are two big projects. One is the James Webb Space Telescope. Who has heard about that before? James Webb Space Telescope. Heard about that? Yeah. Okay, good. Good. You should have heard, because it's extremely expensive. And with that I mean something in the order of $8 billion. So this is meant to be the successor of the Hubble Space Telescope. This is a one-to-one scale model, actually, that was, at some point, NASA traveled to meetings with this scale model here. Not real one-to-one model. But then they figured out that even traveling with the model is too expensive, because you need a couple of people there a week early to just set it up. And, well, if your model already takes a week to set up, you can imagine how complicated it will be somewhere behind the moon in space. Okay? So, because you can't launch it in that way. So this will be a big challenge. The idea is that this will start operation in 2018. And I've been heavily involved in one of the science instruments, and they're in the spectrometer part for MIRI. Then the second part, as Raphael already referred to, is the European Extremely Large Telescope, which is currently one of 3 big telescope projects around the world. There are another 2 American projects, the 30-meter telescope, GMT, and the Giant Magellan telescope, GMT. But, so, for the ELT, it hasn't even started construction yet. The idea is that if things go really, really well, it will see first light in about 10 years from now. So this is about the time for you. And then here I'm the principal investigator for an instrument called MITIS, mid-infrared instrument to go on that telescope. Okay, and so we're currently making all kinds of designs for the instrument, trade-off studies, making science simulations of how a galaxy would look like if you observed it with that instrument on that telescope. That makes sense. Yes.
Where is the MI installed right now? Is it stage or is the second one?
Really? Yeah. It's currently at Goddard Space Flight Center in Maryland. And there this is part, there is a big structure that will be mounted then to the telescope here.
Okay.
And to that structure, the different instruments will then be integrated in that structure.
Okay.
So eventually this goes in here and will be launched.
Great.
Okay. So far about my background. Let me give you a few motivations for the reasons for this course. One is that instruments have become increasingly complex, and we're all using them as observational astronomers. People are sure that if you have written observing proposals or gotten some data, or your supervisor asks you to analyze some of the data, we tend to think that the data are perfect. And this is very different from physics. If you go to the physics department and maybe people have an experiment there in the lab, they know exactly what the experiment does, because they build it themselves. And astronomy has, to a large extent, decoupled from that, where we write some proposal, Hubble Space Telescope, please observe something there. And then half a year later, you'll get an email from Space Telescope Science Institute saying the data are ready and you can download them. And then you look, and if there is something that looks like a faint smudge, you say, oh, I found another redshift 10 galaxy or something. Yeah, and then you write a big paper about it. But of course, you need to understand exactly what you're seeing. Maybe it's just a reflection from some other object, or maybe it's not at all the galaxy you were expecting. So it's really important that you understand how the instrument works, how the data were processed, all these things. And this is, of course, has become more and more difficult simply with the complexity of instruments. This is just one instrument at the BLT telescope. There's no person, but this is about 2 meters across. Right? And you see many pipes and I mean, I've just been checked to see one of the new instruments for the BLT called Muse, and it's huge. Right? It would cover the stage here, and it has 24 channels and lots of pipes. It looks like, well, have anyone seen the Matrix movie? Yeah. There is when they go, well, the travel through I'm not even sure what it's called, but there are all these metallic structures and pipes and so everywhere. And this is exactly how the instrument looks like. And it's covering the focal plane. There are so many things. Calibration is so important. If you don't do that, then you may end up with artifacts. If you don't do that, then you write the wrong paper. Same for the detectors. Some instruments, even when you propose for an observation, they'll ask you how you want the detector to operate. Whether you want to have it put, in what form you want to read the detector, or how you want to map the sky, all these things. And there are lots of experimental setups, in particular when it comes to adaptive optics and other techniques on the ground. Here we see a laser guide star. This is a real laser guide star, not like the one I've seen here from the airport on Sunday night. From the mountains here somewhere, there was this big light spot. But it's not so much different actually when you look at it, only it's narrower and brighter. But, so then, and for bigger telescopes, you will not have just one, you have maybe 5 or 6 of them, and they all need to be aligned, and it gets fairly complicated rather quickly. And then, yeah, as I said, the data analysis has become increasingly demanding, of course. So I'm copying here just to do Richard a favor, colleague at Leiden University. He's usually hunting high redshift galaxies, and he's often been, I'm not sure whether he still is, but the record holder in terms of highest redshift objects. This is already an old slide. This is a business like finding exoplanets. As soon as you write down the number of known exoplanets, right, then it's already outdated. But I'm not even sure. So this one, he says that the dim object here, and yeah, I'm not sure you can see it. I promise there is a red spot. So that compact galaxy that already existed 480 million years after the Big Bang, so only 4% of the universe is currently. And of course, these kind of objects or science programs will become more and more interesting in the future. Big telescopes like the ELT or the James Webb Space Telescope. People want to see the first galaxies in the universe. Like how from the whatever, after recombination, how the first structures form, how the first galaxies form, and see the first light stars maybe. And well, you will certainly get something that's even fainter than this one here. And there won't be probably that many, so you really need to know, is this true, or is this just an internal reflection maybe from that galaxy? Or a detector artifact? Okay, so you have to understand. Yeah, okay. So, let me say what topics. This is of course a wide field. We only have 2 weeks, and not even every day, so there has to be a selection of topics. If we think what happens in nature, we're here. I'll show you in a second. Let's say there's a galaxy. So there's of course what's happening in this galaxy. The physics of the object is not part of this course. This is what all the other astronomy courses are about. Then, well, you have the radiation that's traveling through space. Maybe you see some dust, and well, certainly there is something like the geometrical laws that were also discussed this morning. At some point, it will hit the atmosphere. So we're, for simplicity, yeah, we'll take the atmosphere with us in this course. And this part here is actually what Elena's course is about. So the left part are the morning lectures. And now we have the light traveling through the atmosphere. We have to collect the photons using a telescope. Maybe we use more telescopes to get better angular resolution, and then we call them interferometers. Because of the turbulent atmosphere, we need some correction technique called adaptive optics. The whole thing here, all these components contribute to the way the image is formed. I mean, ideally, if this were a star at infinity, you would only get the delta function here, mathematical, intrinsically small point. But that's never how a star looks like. Not that you would see the star in terms of like we see the sun. It's not resolved, but it's also not a point. And that's because all these components here contribute to how the light from a point source is actually then showing up in our detector. And then we can have, if we want to know the spectral information there, we can add some spectrometers here. Then finally we add some detectors, which is a very important part. When I was a student, I always took detectors as granted, and I didn't worry much about them. No. But the detectors are really one of the key components of why we know so much about the universe as we do now. If you compare it with photographic plates, I mean, we wouldn't be doing what we're doing today if we still had to work with photographic plates. They're way too insensitive and have other disadvantages. So detectors are really key to getting high quality data. detection. Unfortunately, not all of the faint objects just jump at you when you look at the data. Right? They're usually buried under lots of noise and other image artifacts. So you need to really dig out the information. And so you need to worry about the statistical significance and quality of your detection. So and then, if we look at what's plotted here, and just, we can argue about this, maybe this is a bit random, but I thought to put some structure in there. Let's say we need some background information to be able to follow the discussions in the later parts of the course. So in the background, I put the atmosphere, I put the image formation, and the signal to noise of the detection. So these are essentially the first two lectures, giving you a bit of a sort of the context, because all of the rest will always refer to either the turbulence or the noise, or again, image formation is very crucial, and for that I would like to say a few words about Fourier transforms and why this is relevant. And then we have some fundamental devices for observational astronomy. And the most important fundamental ones, which I would call a technique, it's really, I mean, without it, you have nothing. It's are the telescopes and detectors. And then in order to accomplish certain specific goals, you have some special observing techniques. Okay? Like, for example, interferometers, when you really want to get the ultimate angular resolution, the best image sharpness you can get, or adaptive optics to get rid of the turbulence, or spectrometers to give spectral information. Okay, so this is how I structured the course. And, well, you know, we have the afternoon sessions from 4 to 6. Oh, we will still be awake by then. And so we're here now, and today, after the break, we'll discuss atmospheric properties. So everything that, the good and the bad things, but actually I'm not sure there are many good things about the atmosphere, apart from the fact that it keeps us alive. But for astronomical observations, there is, of course, many things that affect the way your data look like. So we need to talk about this. Of course, you can say, I don't care about this, I'll launch everything into space. But then it makes things also, whatever, 50 or 100 times more expensive. And so most people use ground-based telescopes for that reason. And so tomorrow then we'll continue with Fourier transforms, signal to noise, and on sampling, because that's important, of course, when you on the instrument design and how you well, spread your spectrum or your image across the detector. And then on Thursday, after the one-day break for you, I think, I would like to get back to talk. I'd like to start with optics and telescopes. So basic optics that makes sure we all understand when we talk about telescope optics, but then also some aspects about modern telescopes, and on Friday then a summary of all different detector types. So some background of detectors, and CCDs and infrared detectors and bolometers and things like that. And next week then we'll start on Tuesday, Monday's a holiday, talking about interferometry, both at optical and radio wavelengths. I think it's important to have an idea of the general principles and limitations of interferometric methods. Adaptive optics, as I said, is important. I mean, I don't think that there's any large ground-based telescope larger than 4 meters nowadays that people build without including an adaptive optics system. And then finally, some words about spectroscopy, about general things about dispersion and so on. Okay, this is the course outline, but of course, if you have a very specific topic that you always wanted to know more about, that you think somehow you let me know. Okay, any questions about this schedule so far? So, how do we do about studying this? You may have seen, if you already got one of the copies out there, that I have presented most of, well, unlike Elena, I'm not using the whiteboard a lot. So all of the material is in the slides, and you have copies of all the slides. Okay? So in principle, the slides are your study material for your class. And also, the tests are only about what's written on the slides. So if you take the slides at home, or wherever, you'll read them again, and you should be able to remember, or if you remember it, there should be no problem to do the test without any problem. If you want to read more about this, I recommend this book here, Measuring the Universe by George Reiki. It's a very recent book. I think it came out last year only, almost last year. And which is listed here, table of contents, which overlaps largely with what we're discussing. I'm not following this book, but this is for further reading. This is a good recommendation. And I have a copy here. Actually, I could pass it around. At some point, I'd like to get it back. but maybe you can convince Parker to get a copy for the library here.
It has been already called by Bob in Amazon.
Okay. Of course, there is a lot more literature, and as well, you saw this is the course. These are important aspects, but there's sort of a patchwork. It's not like in the course of radiative processes that you can develop it from first principles and go further and further. I mean, spectrometer has nothing to do with adaptive optics, apart from the fact that there are both techniques that you might want to use at some point. So most of the literature is very specific on either topic, and I should send you these slides so we can post them on the web. I think there is no need to have handouts, but just for further reference, if you say, well, I really want to know more about radio astronomy or whatever adaptive optics, here's some reference for further. Okay, what are the prerequisites for this course? Well, you should have a solid math and physics background. I assume you have. Also some background in astronomy. And I don't think it's actually necessary to understand precisely, in many cases, what I mean, it's not that you need to know all about galaxies in order to understand this course here, but if you have no background in astronomy, then you may not understand the relevance of all that. Right? So in order to put this all into context, I think it's good if you have some background in observational astronomy. And then, of course, you should have also some interest in the topics and curiosity. And I encourage you to ask questions in general, and of course also with regard to the tests. Okay, so I recommend you ask questions whenever there are any. When we discuss the atmosphere afterwards, if there's anything unclear, better ask now. You can also ask me tomorrow morning. And but you should ask me before tomorrow 2 o'clock, because then we'll have a test. Okay, feel free to ask in Spanish. But any language is fine as long as you ask if something is unclear.
Yes.
Yeah. So finally, the test, don't worry too much. It will be short. So I thought maybe a multiple choice test is the easiest thing, because there will be a lot of material in the slides. It's not like in Elena's course, it's important to have a fundamental understanding. In this observations techniques course, it's a lot of facts, principles that you need to have understood. But if you forget the name, how it was exactly called or so, that's not a disaster. So that's why I think the multiple choice test is actually not a bad, usually I don't like it, but in this case, it's not a bad way to probe whether you remember some of the things I told you. And so you'll get one sheet with 10 multiple choice questions on it, and each one has 4 answers. And you just read it. The question is usually very simple, 1 sentence or so, and then you just have to indicate what you think is the right answer. Now, the problem, of course, with multiple choice tests is that if you give it to your grandmother, she will also have 25% correct. Right? So there should be some punishment for just randomly crossing answers, and that's why I like to subtract half a point for an incorrect answer. So don't gamble. And then the final grade is just the average of the tests. And obviously, you should not use the handouts during the test, because the answers is of course in the handouts. Okay? I think this is for 10 questions. If we say 10 minutes, 1 minute per question, I think just to read it and make your cross here, that should be fine. So let's see that we can do everything in 15 minutes. Okay, and that's it. Until after the break. We start at...
Yeah, I have a question before leaving this first presentation. It's, if somebody here is interested and follow this path, like somebody like you, what should he stress in this formation? What things he should take more attention in order to work in instrumentation and observation astronomy?
That's a very good question. I think in the bachelor program, usually it makes no difference. I mean, you should not necessarily. I mean, if you already know that you will never attend any other courses than whatever some cosmic string theory, then maybe that's not the right approach, right? You should be open to observational aspects, not just pure theory. Although, of course, I mean, if you manage to do great work in theory, you're a smart person, and you will also do well in these things. But so generally, you just follow the courses here. If the master's program phase, typically, you should, if there is you should look if there is an opportunity to do some research project on an instrumentation topic, right? I realize this is more difficult if you have an observatory, which means that maybe the faculty should see if there is some exchange with other observatories. That not necessarily like anything that as telescopes and instruments may have projects, and they're usually happy to have students who help with the work. It's more a problem of defining the topics and supervising them properly. But in essence, many of the students, I mean, the main requirement is that you have to be smart. And then you can learn everything. And you can even learn it during a PhD. So if you don't have, how do you say, 2 left hands, the expression here, 2 left hands, well, meaning that you're not very skilled with handling things. But I shouldn't say it with Helena because I know that she was that. So, yeah, many things you can just learn in your PhD, and then it is important, I think, that you do this work within a group that does high-quality instrumentation during the PhD. And then afterwards, I think the job perspectives are not bad. Obviously, there are a lot fewer positions in instrumentation than in observational astronomy, just by number. There are so many observational astronomers. On the other hand, many of the projects are planned for 10 or 15 years in advance. They have a long duration. And they need people, no matter what unless you cancel the project, no matter what the economic situation is in the country, they go on, they have to hire people. What's happening sometimes, maybe Rafael, you can jump on it, right, for a postdoc in the US. And my feeling was that many institutions who never worried about postdoc jobs or so said, sorry, we don't have funding for some of them. There was very, very little money from the NSF, and NASA had some cuts. So they cut the positions for observational astronomy, for data astronomy, were just people working on observations. Whereas people working on instrumentation in particular, they're always needed, unless you kill the whole program and say, okay, close the observatory. So there are fewer positions, but I think if you're really good, you will always find a job in that field.
Yes.
Yes.
I read in the part of the evaluation of it says that if you got a correct question, you will get 1 point, right? A correct answer counts 1 point. For the correct answer, 0.5 will be subtracted. So, for example, if I'm not sure what to answer in a question,
You just don't do anything.
yeah, it's better than trying to.
It's better not to, yeah.
That's it. No, but be brave, be bold.
Yeah.
Or just with the handouts.
Yes.
Really.
That will be.
That's, I mean, that's the whole point, right? The incentive of subtracting points was that you should increase your level of certainty by reading the handouts and not just be brave and gamble. In fact, on the other hand, sometimes you can, if you don't know, you can, just by common sense, you can well, take out 3 answers that don't make any sense. And even if you don't know, the one that's left is the right one.
But sometimes you get you take out 2 and you get 2. So
Yeah, that brave and gambling part comes back.
You're allowed to take another person's probability before you.
I have read the first test. I have read the first test, and it's really solo from the hands-out. So it's my work.
La idea es que aprenda, entonces miren las slides la noche anterior y debe ser suficiente para aprender el concepto. Okay, what time will we start?
Okay, so let's take the break in advance. Entonces tenemos media horilla de descanso para que se despierten y se laven la cara y a las 4:15 para